Hi, my name is Dr. Richard A. Venditti, and I'm going to give you an introduction to the environmental life cycle assessment. Okay, I'd like to start to talk about what drives mankind. And there's a very famous theory called the tragedy of the commons. And basically what it says is that each person is individually going to think about how they're going to make their life better and be healthier and have more resources to help themselves. And if we all think the same way, that each person trying to kind of preserve themselves and keep them as wealthy as possible, what happens is all the common resources that we share, like land, water, and air, what will happen is we will just consume all of those. And this picture gives you a nice example of what happens. When you look around and you look at the air or water, the ocean, you see an infinite amount of space and area and resources. And so generally what a person thinks is their individual activities aren't going to impact this immense amount of resources. But that's not always the case. You know, the other thing is I talked about individual people, men and women, and the tragedy of the commons. But if you think about companies, they're similar. Companies have a lot more tools, resources, and capital to actually make new things, and so they can actually consume a lot more resources. So in the past, typically companies would take air, water, and land, treat them as commons, as an infinite source, and then make their products. And their objectives of these companies are to minimize the costs to manufacture and to maximize the appeal and the demand for their products. They're trying to maximize profits. And you can see that these companies also can be taxing on the commons. Here's just a good example. This picture right here shows you what happens when the tragedy of the commons is actually occurring. Basically, what we've got here is a real picture of a city in China, and each individual has almost an insignificant contribution to this pollution, but as a total, you can see that pollution adds up and really can cause some problems. In the United States, historically, we had the same kind of problems. Back in the 1800s through the 1900s, most manufacturing plants were built on top of on the side of a river, using the water in the process, and also using the water to maybe turn a wheel and get power. And so back, at the turn of the century, between 1800 and 1900, these mills would just dump all their waste into the rivers without any treatment at all. They look at the river, and the river looked like it is an infinite source of water, an infinite source of dilution, and the little pollution they put in wouldn't cause problems. However, the pollution did add up, and as these mills accumulated more and more mills and higher production, the amount of pollution in the rivers was so great that at some point, some of the rivers caught on fire. They were so polluted. So just imagine that, a flowing river catching on fire because of all the pollution. The other thing, so that's one kind of concept we should think about, the tragedy of the commons. And the other thing is uncertainty. What don't we know? So in general, we know a lot, but we don't know everything about every process and how it impacts the environment and people. So just to give you an example, this shows an advertisement about what we didn't know, perhaps, maybe 80 years ago. It shows, cigarettes as a healthy alternative, as healthy for people, and then doctors recommending smoking, and is a part of a healthy lifestyle. And back then, we really didn't know all the damaging effects of smoking. And so you can actually ask yourself the same question about what we don't know right now. For instance, our cell phones. We think that they're not harmful to human health, but do we really know that? There have been some studies that are investigating whether there's an impact on the radiation and the electromagnetic waves in a phone on our brain. We're holding up very close to our brain. Maybe in 50 years from now, we'll think of phones in a different way than we did now. But environmental life cycle analysis also has to kind of be tempered by this uncertainty. All right, now here's just a trend here. What we're understanding is that the Earth is actually going through a global warming period. And what this graph right here shows is in red, that's the temperature of the Earth. And you can see how it's been cycling over hundreds of thousands of years. What many people are really concerned about is that in the recent era, we've had quite a bit of temperature increase, which is a natural cycle. But on the other hand, in the blue curve, we see carbon dioxide concentrations in our atmosphere, a global warming gas. And what you can see is in the last 40 years that there's been a spike in carbon dioxide in our environment. So you can see it from here rising all the way back up to here, over 300 or so parts per million today. And the correlation between the carbon dioxide and the global temperatures are causing many to be very, very concerned that this CO2 increase will prompt a temperature increase with lots of very damaging effects to our Earth. And in fact, these graphs here show three of the most common greenhouse gases or global warming gases: carbon dioxide, methane, and nitrous oxide. And you can see over this time span, which is about 10,000 years, the concentrations of these gases have been pretty constant. But then in the industrial, after the Industrial Revolution, we see this spike. This is called a hockey stick graph. And basically it's this spike, and it's in carbon dioxide, methane, and nitrous oxide. All of these have spiked, and we're very, very concerned about how this is going to impact our environment. So we know that society needs products. We need products to live and to be healthy. And oftentimes you hear about this concept about a green product. Well, I'm here to tell you that there's really no such thing as a perfectly green product. Every product we use or service we use taxes the environment, okay? And so what is important is that we should have some way to rationally, scientifically choose between different options that will allow us to live healthy and comfortably. And so life cycle analysis, or environmental life cycle analysis, allows us to rationally choose between those options based on the environmental impact that those two options would have on the environment. So we use environmental life cycle analysis as one way to try to choose between different options. All right, now there's an interesting thing that's happening. Our population is going up. The quality of living is also increasing, okay? And so if you take a look at this master equation, the total environmental impact of society is equal to the population times the quality of life, and we measure that in GDP per person, times the environmental impact per unit of GDP, or how much we consume. So in this equation, we know the population's going up, GDP per person is going up. Then the only thing that we can do to affect society's impact on the environment is to maybe improve the environmental impact per unit of GDP, or the efficiency at which we live. So environmental LCA helps us understand for two different options which one will have the lowest environmental impact. So this is really what most people think of as the only possible solution to the increased impact of society on the Earth's environment. All right, so the other thing we need to talk about is about sustainability. And there's a very simple definition, I think, that really helps us understand what sustainable means. And basically the definition says that if something is sustainable, then it should allow us to supply our current society's needs without harming the environment or future generations' ability to meet their needs. Okay? In other words, we want generations past us to live at the same quality of life that we did. Okay? And you can think about sustainability in three terms. You can have social, environmental, and economic. All of these three things are important in the dimension of sustainability. Today, what we're going to do is we're going to focus on environmental sustainability. Okay? So amongst different options to meet our needs, how can we choose the best environmental option? Environmental lifecycle assessment helps us do that. All right, so let's get into lifecycle assessment. What is it? Okay? Simple definition. It's a tool to assess the potential environmental impacts of products, systems, or services at all stages in their life cycle. So that's a very important and really well fleshed out definition. A lifecycle assessment, there's standard methods of doing it, and when you're a company and you want to promote and you want to make an environmental statement, the most trusted way to do it is to use the standard methods from ISO, for instance. Okay. So when we do a life cycle assessment, we can do it of a portion of the life cycle or the entire life cycle. Cradle to grave is probably the most robust way of doing a life cycle assessment, and probably the most important. So in a life cycle, what we do is we are going to look at different operations, from raw materials to the production of a product, transportation anywhere along the life cycle stages, the use of that product, and then finally the disposal or recycle or the end of life of that product. So we're going to consider all those life cycle stages. So we're taking a very systems approach to the impact of a product or service over its entire life. Now, for each one of these operations, what we're going to do is we're going to tabulate all the energy inputs, all the raw materials inputs, and then all the wastes, whether they be solid, air, or water, at every different stage, and we'll add them all up. And in the end, we'll have environmental impacts of the product or service cumulative through its life cycle. All right, so the idea here is that we want to have companies that consider a life cycle approach to their products. So they will look at all the different operations, but we're hoping that they will also consider the use of air, water, and land, and the pollutants that we put into it, and try to minimize that. So we're hoping companies, through environmental LCA, are trying to minimize their cost and maximize the demand of their product, but at the same time minimize the environmental impact. If they try to minimize the environmental impact, then their products will be considered more sustainable. And then more people, because they're sustainable, will want to purchase that product over another product that might not be as green as that product. So it makes sense for companies to not just be sustainable to be sustainable, but it helps their business strategy. All right, just as a kind of a current event, that's what's going on. Well, this happened in 2017. Volvo was announced that they're going to be the first automaker to offer electric or hybrid cars only. So what that means is that they won't have any traditional petroleum-based cars, 100% petroleum-based cars. And basically, what they're thinking is that this is going to help them in their marketing and their demand of their products. By putting the emphasis on the environment, they're hoping that people buy more of their cars, as well as hopefully there's some environmental improvements. Okay, so at the same time, that's a company doing something. But there's also, we know, in many countries, governments that are doing something. Governments can be a very powerful influencer on how we live. And basically, what this slide is talking about is that there have been some standards for U.S. automobile fleets set up by the government that all companies have to obey. So you can see that companies have an interest, as does government, as do people. Everyone really has an interest. Okay, here's another example. So what happened here was an environmental life cycle analysis was conducted on electric versus gas-powered cars. Okay, and this is a relatively robust and, for the most part, a very fair assessment of the two different options. Okay, they did a cradle-to-grave analysis, so they incorporated all of the different important life cycle stages, and then they considered the emissions involved in using the car, making the car, resources consumed in manufacturing the car, and then they looked at a range of environmental impacts. And you can see that they considered greenhouse gas emissions, acid rain, and other types of environmental indicators in their study. Now, the interesting thing is that the conclusion from this LCA was that electric cars are indeed better for the environment. That was the conclusion of the study. However, what I want to tell you is that we really need to really dive deep into conclusions like that. So if you go into the study and you look at it, what you'll notice is that there's different environmental impacts, and there's electric cars aren't always better. So, for instance, the environmental impact of making the electrical vehicles is greater than for making gas and diesel vehicles. So that's just one stage of the life cycle, but it was a negative one. However, for the electric cars, lower energy consumption, lower use of resources, lower greenhouse gases, and lower ozone pollution during use was a real benefit of the electric cars. Okay. However, in the study, they assumed that the electric cars were going to be charged with significant amounts of energy from fossil fuels, so that's a negative. However, and then the last point is that in some environmental impact categories, like acid rain and algae blooms, the electric cars were worse than the petroleum-based cars. All right, so now let's get into environmental life cycle assessment, and let's kind of look at all the different parts of a study. So there's really four parts: goal and scope, inventory analysis, impact assessment, and interpretation. And we're going to go through all four of these and talk about the important parts of each one of these parts of the LCA. All right, so when we define a goal, what we have to do is say, okay, what are we going to apply? What is the application for this study? How are we going to use the results of this study? And who are we going to talk to? What is the audience? So our goal has to be very well defined in order to kind of define these kinds of things. We also want to include the reason for why we're doing this study. Why is it needed? Do we want to prove that one product's better than another? Do we want to find out how bad one single product is? Do we want to compare life cycle stages? All these are important in the goals. Now, another important part of the goal and scope is what's called the functional unit. We have to define a functional unit. Functional unit is the quantified performance of a product, and it's used as a reference unit, okay? And really what it is the function that is delivered by the product, okay? So that's really the important part. So, for instance, let's look at a functional unit for drinking containers. If we wanted to compare 100 disposable paper cups versus one glass container washed 100 times, then the functional unit would be 100 drinks delivered to a person, okay? And it doesn't matter whether you get it from a disposable paper cup or you get it from a glass container. The functional unit allows us to compare these two different systems on an equivalent basis. So you can see that you want to, if you're just going to use the paper cups one time, you need 100 paper cups. And if you use the glass container and assumed it broke after 100 times, then you'd need one glass container. So the functional unit allows us to have a fair comparison between systems. Very important part of environmental LCA. All right, so the goal and scope we just finished talking about. Now we'll talk about what's called the inventory analysis. Now, the inventory analysis, simply put, is the mass and energy balances of a certain product over all of its stages. So, for instance, let's just say we have a product here. We need raw materials, we need to manufacture the product, transport it, use it, and then dispose of it. So for each one of these life cycle stages, there's going to be different operations or processes. So if we just kind of magnify one of these processes down here, we've got a process. For each one of these processes, we have to clearly define what raw material inputs are coming into the process, how much energy we're consuming by the process, and then we're going to want to know how much product is made, and then how much emissions to air and water, and how much solid waste is produced, okay? So all of this in combination is a mass and energy balance around this process. And what we do is we take each one of these processes, and then we kind of add them all up. And then what we have is the overall mass and energy balance of our product system, okay? Now, there's two important flows that we have to distinguish. One are flows that go within the technosphere. So the technosphere is the built environment that mankind has created. So for instance, if I build a product like a phone, and then I move it over to another building in order to prepare it to be transported, that is all within the technosphere. So because it's all within the human environment, we do not consider that as important as the other type of flow that we'll talk about, which is called an elementary flow. Now, elementary flows are very important because an elementary flow is where we actually take something from the environment or we put something into our environment. So the environment, these are called elementary flows. So an example is if we take coal out of the ground, that's an elementary flow. And if we, let's say, burn some kind of fuel and we have carbon dioxide emissions that go out a smokestack but then go into our air, that would be considered an elementary flow because it's going into the environment. So basically we define these elementary flows as a material coming from the environment prior to any human processing, or a flow going into the environment, and that is going to be after any mankind processing, okay? In other words, we're taking from the environment and we're putting into the environment. Those elementary flows are really the things that affect the environment, okay? So when we talk about environmental LCA, what we want to do is from our mass and energy balance, we're going to want to tabulate all our elementary flows. These are the ones that actually impact the environment. Very important concept. All right. Now, how do we usually do these mass and energy balances? In some cases, if we have knowledge about, like, let's say, a factory, we can actually go in and make measurements and we can figure out, okay, how much raw material is coming in, how much energy are we using, how many emissions are we producing. But most of the time, we don't really have that information about the factories. So what we do is we rely on databases that have tabulated many, many types of processes, and they give us the mass and energy flows in that process. And we use that database information in order to do our LCA. So one of the most famous ones is the United States Lifecycle Inventory. So it's called USLCI. And that USLCI has exactly what I said it has. It has a bunch of different processes, and it's got all the input and output flows. So let's just take a look at an example. So this is an example where we're producing container board to make boxes to, ship things. And basically, if you go to that database, and you can look this up on the web, it's free and accessible, what it will first start to list is all the inputs to the process. So you can see that to make this container board, you need coal, you need water, you need some fuels, and you need some other things. And this is just an abbreviated list, but you've got to have a lot of different inputs, okay? And what you'll see here is that they have two different inputs, product flows and elementary flows. The product flows come from somewhere else in the technosphere, Okay, so they don't directly impact the environment. They indirectly impact the environment. And then, so the product flows come from the technosphere, and then it identifies elementary flows. So you can see here that we have an elementary flow of water coming into our paper mill to make our paper. So that would directly impact our environment. Now you might ask yourself, well, why isn't the coal an elementary flow? Don't we get coal from the ground? Well, yes, we do, but this type of coal has been manufactured. So we took the coal out of the ground and then we brought it to a mine where we might have ground it, we might have purified it. We did a lot of processes. So it's actually the mine, the coal mine, or the coal processing plant is actually part of the technosphere. Now, if you go to that coal mining operation, then you would probably find an elementary flow that would say coal out of the ground, okay, where it had not been processed before that. So anyway, it's very important that we emphasize that elementary flows are what affects the environment, and we've got to tabulate all those, and then we're going to use our elementary flows as our calculation for environmental impacts. All right, now this is the same container board model from that database, but this is all the outputs. And what you can see is that there's carbon dioxide that is sent to the environment, and those are elementary flows. So that's very normal. And then there's other gases like carbon monoxide at a low level, but still sent to the environment, so it's an elementary flow. Then we have the container board that we produced, and notice that's a product flow. Now it's a product flow because it's going to go to somewhere else in the technosphere. So eventually it might be thrown into a landfill or thrown on the side of the road as litter. Those would be elementary flows, but at this point we're just going to use it as a product flow because it's going to somewhere else. This will probably go to a converting operation where they make the box and then they fill the box with the product. And a very important part of it is that this process, all these flows are on the basis of 1.11 kilograms of the container board being produced. So that's a very important one. It's bolded because it's the main product, okay? And so all these other numbers are ratioed properly to the product flow. Then you can see more elementary flows that are outputs. Things like water, other gases, particulates into the air, and then there should be solids that actually go into to landfill and things like that. And this is also an abbreviated list, but this gives you an idea of what is involved in a life cycle inventory. Again, if you don't have the personal knowledge about these kinds of flows within a factory that you work at, then you have to use the database and trust that this data is representative of your product of interest. All right, so we've talked about the goal and scope of our LCA, and then we talked about the mass and energy balances and the inventory analysis. We mentioned that the most important part of that is to tabulate all the elementary flows. Now, the third part is the impact assessment. In this case, what we're going to do is we're going to take the elementary flows and we're going to calculate what is the impact to the environment. All right, so the impact assessment, the definition. It's the part of the LCA that predicts the magnitude of environmental impacts for a product or service, okay? And of course, like I said, elementary flows, whether they're material inputs that are taken from the environment or pollutants that we put into the environment, we're going to track all those elementary flows to calculate our impacts. All right, so the way that we assess the environmental impact is we use models. Okay, so one of the most famous models from the EPA in the United States is what's called Tracy. And that Tracy model basically calculates environmental impacts for us. So it will calculate global warming, acidification, and all of these if we input into that model the elementary flows. Okay. What you see here is that it has some environmental impact categories, but it doesn't have all environmental impact categories. So for instance, I'm looking for sound pollution. I don't see that. I'm looking for radiation. I don't see that. So there are many different tools. This was just one example, and I'll go to the next slide. This is another modeling system, and this is called Impact 2002 Plus. And what you see is that it also is going to take the elementary flows from our LCI and calculate some environmental impacts like this. And what you'll notice is that ionizing radiation, that was an impact we didn't see in Tracy. But if that's important to you, then you're going to want to maybe choose Impact 2002 as your model. So there's many, many models. There's probably 20 or 30 models or so. And they all have a different set of environmental impact categories. In many studies, they'll use more than one model in order to get all the impact categories that they're interested in. All right, so what are these models? All of these models like impact and recipe and all these other models, what they have is a set of what we call characterization factors. It's very, very simple in the sense that what we do is we take our elementary flows. Let's just say we have 2 elementary flows for this product, carbon dioxide and methane. And let's just assume we have 1 kilogram of each. So these are our elementary flows. We put that into our model, and our model has these characterization factors. And what the characterization factors say is some pollutants are more potent than other pollutants, okay? So for instance here, we're going to take 1 kilogram of carbon dioxide, we're going to multiply it by 1, and then we're going to get what's called 1 kilogram of CO2 equivalent. And that's going to be a measure of our greenhouse gas or our global warming. Now, let's just say in this process we also had 1 kilogram of methane that was emitted. Well, what will happen is we look up that characterization factor in the Tracy model and we get a number, a characterization factor of 21. What that means is that methane contributes to global warming 21 times more than does carbon dioxide. So what we do is we multiply our 1 kilogram by 21 and we get a number 21 kilogram CO2 equivalent. Now for every environmental impact category, there is some unit that is assigned for that impact. And in this case, what we're going to do is we're going to say, we're going to equate all these different chemicals to carbon dioxide. So, of course, 1 kilogram of carbon dioxide has a 1 kilogram carbon dioxide equivalent. But the methane, that 1 kilogram, is going to have 21 kilograms equivalent CO2. Okay? Now, what all these characterization factors allow us to do is add up all the different gases. You could have 50, 100 gases or so. All with, you just can't add up different gases, but once you multiply by the characterization factor, get them all into the same equivalency unit, then you can add up all of these, okay? So for this product that I just kind of assumed had 1 kilogram of this and 1 kilogram of that, our overall global warming potential effect is 21 kilogram CO2 equivalent. Okay, very simple process, but this is the exact same thing that happens for global warming, for acidification, for eutrophication, for all the different environmental impact categories. So let me just kind of go back. You can imagine that if you're using Tracy, there's a whole set of impact characterization factors for global warming, and then there's going to be a whole different set of characterization factors for acidification. And then you've got human health, you've got respiratory effects, eutrophication, that involves the depletion of oxygen in water bodies like lakes and rivers, ozone depletion, ecotoxicity, and smog. So these are all the impacts for Tracy, and there's a unique set of characterization factors for all of these. So basically, again, let me review. You take all your elementary flows, you look up their characterization factors, or you have a computer program that does that for you. It calculates equivalencies in all these different categories and then adds them up. So what do the results look like? Here's an example of a cradle-to-grave environmental impact of making bioethanol from woody-type plant materials, okay? And what you see here is that all the elementary flows were tabulated, and then those went into the Tracy modeling system. And then you can see what are the environmental impacts, right here, all the Tracy impacts for making bioethanol from either eucalyptus, natural hardwood, pine, switchgrass. What's very confusing about this is in some cases a product, let's say bioethanol from eucalyptus, it will have some environmental impacts that are higher and some that are lower than some other alternative product, like natural hardwood bioethanol. And so really, one of the issues becomes how do you get, that there's multiple impacts, environmental impacts, and then not all product comparisons will give you one product that has an improvement on all of them. So what do you do when product A and product B, it's 50-50 split? Which one's better for the different environmental impacts? That's an issue. All right, so one of the ways, and this is a kind of a controversial way to compare these different products, for instance, all these different products here, is to calculate a single score. So what is a single score? A single score takes up all the impact category results, like global warming, acidification, all of those, and what we do is we normalize them, and then we multiply them by a weighting factor, okay? So the normalization divides the impact of that product by some reference amount of the impact. So for instance, the reference amount of the impact might be the total amount of global warming potential that the United States as a country emits every year, okay? And so when we divide by that, we kind of get an idea of how critical or how significant the impact that our product has relative to some reference, maybe a country or per person or globally. So the normalization is the first step, and then the second step is weighting. In weighting, what we do is we use weighting factors, multiplicative factors, on the different environmental impacts like acidification or global warming, and basically we kind of say which of these environmental impacts we think are more important. Okay, now there's a problem there, because when we think of them as being more important, that's a subjective opinion. So basically we're making an opinion based on our values and our history. So a lot of people don't like these weighting factors because it's an opinion, okay? So anyway, we take all our environmental impacts, we normalize them and weight them, and then we add them up and we get a single score. So let me just give you an example. In this example right here, we're looking at 3 different types of shoes, and for this environmental analysis, we measured these impact categories. So this is a little different from Tracy, but just imagine that in this example, these are the environmental impacts we have. And this is the raw data, okay? You can see that we've gotten the global warming in kilogram CO2 equivalent, and we have those 3 values right here. Now, first step is we're going to normalize these. So what we will do is we're going to divide our results here by some reference value. Here we're doing the annual per capita, world annual per capita amount. So this tells us on a per person per year basis how much of this pollutants we do. So we're going to take, let's say, 0.053, which is the abiotic depletion, 0.053. We're going to divide it by that normalization factor, 1.6 e to the 11th. So that's the normalization part. And then what we're going to do is we're going to multiply it by a weighting factor. Now let's look at the weighting values that we're using for this example. In this case, what we're saying is our weighting values, we think that all of these have equal importance. That's an opinion. It may be that somebody else might think global warming is the most important, and I want to have a higher weighting factor. But in this case, we're going to say that all these environmental impacts have the same weighting factor. So we're going to just assign 0.2. You see that all the weighting values have to add up to 1.0 if they're in fraction form, right? So then what we do is we take the 0.2 and we multiply it by the normalized result, and we get 6.8 e to the minus 14 as our result. So you can see that we've taken the raw data, which is 0.053, we've normalized it, and then we've weighted it, and we got 6.8 e to the minus 14. Now, what we can do now is that each one of these environmental impacts now have the same units, 1 over per person year. So now we can add all these up, and here we get our single score for shoe A. Our shoe A has a single score of 1.6 e to the minus 13. Now, we can do that for every piece of data here, and then we can add up all these columns here, and we get a single score for B and a single score for C. Now, what you can do then is say, okay, shoe B is going to have the lowest environmental impact, okay? And so you would choose shoe B if all the shoes are perfectly equivalent, except you wanted to have the lowest environmental impact. Now, what's the weakness of this? The weakness is that we have this subjective or opinion-based weighting value. So if I change this around, it might not be that shoe B is the best. So that's why people are a little concerned when you report single scores, because it has some bias or opinion in it. But that's one way to compare different products on a single score. All right, so here's an example of a single score comparison, and we're looking at two different types of pulp or fibers that we make into paper. One is called ECF and one is called TCF. And you can see that if we use a certain weighting scale, this is a weighting scale of the producer of the pulp, what we get is a higher single score for the ECF than we do the TCF. So we would pick the TCF in this example because it has a lower environmental impact. And the other thing that this graph kind of nicely shows you is for all the different environmental impacts, which ones are the most important to the single score. And you can see here that ecotoxicity, carcinogens, non-carcinogens, and eutrophication have the biggest impact in the resulting single score. Now, there's also a user section and an LCA expert. So why we have these is the producer has some opinion and they put in their weighting scale. This is the user of the pulp, and they might have a different weighting scale. So somebody was asked about some user of this product was asked about their weighting scale, and they had a different weighting scale than the producer. And then an LCA expert, because they know so much about environmental impacts and how LCAs are done, they might also have a different weighting scale. So you can see in this case, the overall single scores are different for the same products based on your weighting scale. However, fortunately enough, for all these different weighting scales, the TCF seems to consistently better environmentally perform than the ECF. All right, so that was impact assessment. Impact assessment took the elementary flows, calculated the environmental impacts, and then optionally could calculate a single score. All right, now the last thing in an LCA is the interpretation stage. Okay, so what are we doing in an interpretation stage? In interpretation stage, we're trying to understand what are important about those findings. Are there strengths in our analysis, and are there weaknesses? So we're looking at our results and we're saying, hey, have we been very complete? Have we looked at all the life cycle stages? Have we looked at all the pollutants? Have we looked at all the raw material inputs? We look at how sensitive our results are to some of the assumptions that we've made, or some of the processes that we've used, or some of the pollutants that are in there. We try to make sure all our calculations are consistent and all our material and energy balances work. We want to check to make sure that our conclusions are valid conclusions based on the results of our report. We want to tell people about the weaknesses. A lot of the times it's assumptions or bias that we might have. And then finally, in our interpretation, we want to say, okay, based on our results, what are the recommendations we can give to other people in order to use these results in a nice way? All right, now the last thing I'm going to talk about are example uses of LCAs. Okay, really there's three different example uses of LCAs. The first one is we have different products, we equate them using the same functional unit so that it's a fair comparison, and then we look and see which of these products is environmentally preferred, okay? And like I said, oftentimes, because there's multiple environmental impact categories, it's not very clear. One of the solutions is a single score, but again, that single score is biased by some opinions. Now, another thing that we can do in LCA is we can do a hotspot analysis. For instance, if we ask ourselves, a radio, let's just say, for example, a radio, what is the environmental impact of that radio? Well, and can we improve it? So what we could do is we could say, okay, let's do a LCA, and what we do is we keep all the life cycle stages separate. And what we can find out is which one of those life cycle stages is the most critical to improving the environmental impact of that radio. If you think about it, what are some of the stages? Well, the raw materials, how does that impact the environment? The manufacture, how does that impact the environment? And then the use of the radio, because the use of the radio consumes a lot of electricity, right? And then you have end of life, and then there's transportation too. But it may be that because the use stage uses so much electricity, that where society should spend their time is trying to improve the electricity efficiency of that radio. Or maybe the study finds out that, well, no, it's really end of life. When we throw that piece of the radio away, that has environmental impacts that are much more important than use or manufacturing. So we would want to focus our improvements on the end of life. Or it might be manufacturing, then we can do that. So hotspot analysis allows us to identify which life cycle stage or even which life cycle stage pollutant is the most important to improve. And the third one is understanding communication. Oftentimes we use LCAs to communicate environmental impacts. Okay, so one of the things that we can talk about is environmental product declarations. So whenever you see a product that has some declaration about its environmental impact, that's a communication that the company is trying to provide to you in order to actually market and sell their product. So there are different types of environmental product declarations. Some are uncertified, where the manufacturer just stamps something on the product and says, I've got this environmental declaration. An example is 100% recyclable. A lot of times people put, just because maybe it's paper or a certain type of plastic, that is 100% recyclable. They just put that stamp on, but they don't really certify it. That's one way. And then there's other types of environmental product declarations where they list out all the environmental impact categories that a certain model like Tracy would give you. It's very complete, very robust, but it's very difficult to communicate that on a small label or to the general society that aren't experts in LCA. So environmental product declarations, yes, they're good. They can help us make better purchasing decisions. They can, and then they can, really help us choose different products that are better for the environment. However, we have to be aware, some are uncertified, some might contain what we call greenwashing, which is the is exaggerating environmental claims to help your marketing of your product. So that concludes the talk about environmental LCA. I hope you got a lot out of that. And hopefully you can use this in your everyday life to make better decisions and to interpret life cycle analysis.